Let's take a look at how we would use control charts over an extended period to monitor and control our processes as we try to improve them. So these examples are X bar R charts, but if you're studying statistical process control and see all the other kinds of control charts that are out there, the process could be the same using any of those, but this one we're going to take a standard X bar R process control for some variable that comes out of our process as we go on. So we want to use control charts. I'm going to simulate very quickly here a 5-day improvement cycle. It could have been 5 months, 5 weeks, whatever you decide the cycle is. So in the first round, you go off and basically collect your data as you go through your process, and you track your control chart over time. So this might be the look of our control charts and our process after the first cycle. You might have had some out of control limits way back in the beginning as you stabilize the process, but for the most part, the process appears to be under control. So you might go ahead and implement the change you'd like to make in the process if you're looking to improve it over time, and then continue to measure the process using the control limits you had established. What immediately happens is that you notice the process does in fact go out of control in a good way. It's our intent. We're trying to improve the process. So assuming that whatever this process is measuring, we want the number to go down, we can see that since the point at which we made our change in our process, the data points we're tracking now are in fact a lot lower, and therefore obviously the process is not in control. And that's a good thing for us since we were trying to make the process change over time. So what I'll tend to do then is I will redraw my limits at that point in time. I no longer care what the values were or the control limits were before I implemented the process change. I now have a second round of monitoring the process, and I'm watching it behave at a new level, which is noticeably better than the old level. But again, I continue to use process control. You're never done using statistical process control as you go through. At some point, when you're changing the limits, you want to statistically verify that the change you're acknowledging is real, that it's statistically valid. Now, in this particular example, I've drawn the example to be so extreme that you can tell it's a statistically significant sample. But sometimes the change in the process, like a 0.5% change in fuel consumption for a large-scale fleet, could be worth a lot of money, but it wouldn't be as visually obvious in the control chart as you go through. So what you'll typically do is you'll use an F-test, statistical test, to look at the variances of the before and after processes and see if they are statistically significant. And this one is, as long as the F value calculated at 1.49 is greater than the critical value at 131, you know you have a statistically significant sample. In fact, the p-value tells us that there's only a 0.8% probability that we, by random behavior, would have seen the process jump this far had we not changed it. So we're confident that our changes are real and that we can use these new control limits. So we'll simply extend the process and make a second change and then continue monitoring the process. So again, I've improved the process again around 0.47, 48. And now I notice that the process is again out of control, so I can now say, okay, I want to calculate new limits for this process and let the process continue to run over time. So I'm convinced that the process after the second change is in fact a significant improvement over the second round process. I'll run my F-test again to make sure that's true, and in fact it turns out to be true that the changes I'm noting are statistically significant. If the changes weren't significant, I couldn't legitimately change the control limits because I wouldn't be able to explain what was going on. But in this case, I'm happy to do that. So if I've got a significance here in the third round, I can continue on, make another set of changes, repeat the cycle, see the process move down, calculate new limits, and monitor the process over time. Take the F-test to compare the before and after that third step to show that it's significant, and then eventually make another change to the process. I'm constantly changing my process and monitoring my control charts to make sure the process shifts both in the direction I want it to move and that the process stays under control at that new level. So I might have a fifth round process going on that I'll double check with my F-test. So that's the way process control works over time. It isn't usually this visually obvious, and many of these kinds of changes certainly can't be done in only 5 days, but that's the logic of the process going through. If I pull all my data together and do some extra analysis, I end up with charts like these where I'm looking at the entire scale. And notice on the left, the original lower control limit, the red line on the left, is as good as I could hope the process would be when I started. And then on the right, I've got my final upper control limit, which represents the worst I expect it to be today. So notice that the worst I'll get today out of the process on the right is visually and statistically very, very different than what would have been considered my best case back under the original process. And that's the value of statistical process control. So even if management believes the changes are there, you believe the changes are there, you want to be able to show it statistically, that you can prove statistically that you've made significant changes to the process and that it is now stable at its new and better performing level.